Hi, I'm Rosella, and today I'm talking about 17.3 on vector fields. So the definition of a vector field is a function that assigns a vector to each point in the plane or in 3 space. So a common place we've seen that is in the gradient of a function, and let's just do a quick recap of what a gradient is. So this is exactly what it is, and it's in the direction of the maximum increase of the function at a point, and this is based on the partial derivative of the function in terms of x and in terms of y. So like I said, all of them calculate that at an individual point they want to see where the maximum increase is, but if they put it all together it creates a vector field, and that helps demonstrate what a vector field is. So this is an actual picture of a vector field, and if you took physics you might recognize this, and this is a gravitational force field. So if you ever took physics, you recognize the force of gravity as one of the forces that acts upon Earth, and moreover, when it's away from Earth, assume about here is Earth, the force of gravity isn't exactly 9.8. So the force field helps show the relationship between the force of gravity and the distance from Earth. And as you see, all of the vectors, like this one, points inwards towards this little Earth thing, and it demonstrates the physical relationship of distance and force of gravity, in that the closer you are to Earth, the higher the force of gravity, and this is seen as how the vectors get bigger and bigger as they get closer to Earth. And this is in 3 space, but a lot of the vector fields that we're going to be dealing with is actually just in 2 space. And actually, this concept functions a lot different than a lot of the concepts we deal with in multivariable, because it's still a function of 2 variables, but it's represented in 2 space instead of 3 space, because it isolates the relationship between x and y. And also, a 2 space graph is more than enough to show the components of a vector with 2 variables. And although mostly we're going to deal with 2 space, there's still some 3 space questions in which we'll be asked to describe the graph if it's a function of 3 variables, or just write out the equation. So let's look at example 1. So example 1 asks you to sketch a vector field of the 2 space given by this function. And as you see here, it's a force field, and since force is a vector, it's also a vector field. So before we can graph anything, we have to figure out what we're graphing, and the first step towards doing that is to draw a table of values and see what the vectors look like at different points. So I decided to do a table of values with 3 different x and y coordinates, which means you'll get 9 vectors overall, and that should be enough for you to see a pattern. As I said, there are 9 combinations of coordinates, and all you have to do is plug one combination into this equation. And let's just do one as an example. So -1 and -1, if you plug it into the equation, gives you I minus j. So I completed the table of values, and the 9 coordinates produce these 9 vectors, and this will help you plot a graph to see the pattern of the vectors, and you don't have to plot all of the vectors to see a pattern. So before we do that, I want to talk about how you interpret something like this. And basically, I minus j means that for every 1 unit of increase in x, 1 unit is decreased in the y direction. So now you know kind of what each individual vector looks like. It's also important to also do magnitude, which is given by this equation. And if you put the function into the magnitude equation turns out to be this. So you plug in individual coordinates for every point, and that'll give you the magnitude of the vector at that point. And so now you're ready to start graphing the vector field. To do that, first identify the points in the table of values and where they lie in the graph. So I dotted the 9 different coordinates in which we found the vector for, and let's plot it. So again, I'm going to show you how to do that with -1, -1, which is this point right here, and as I said, 1 increase of x equals a negative in y, which looks roughly like this. And now you do that for the rest of the 8 points. So after you graph all 9 coordinates, this is what the vector field looks like according to the table of values. And as you can see a pattern here. So it's kind of like a whirlwind thing. And if you graph all of the points on the function, it'll keep this pattern of a whirlwind just a lot bigger. So now let's move on to the next example. And this one is actually in 3-space as shown here, and notice that in 3-space questions, which is both example 2 and 3, you'll never really be asked to graph it because it would be really hard to graph a vector field in 3-space, and instead this time you're asked to describe it. And let's do this without graphing. So before we describe it, we have to figure out what this notation is, and notice that since we're in 3-space, the coordinates are x, y, and z now, and this equation basically says that it's a position vector at that point, which means that the force at that point of x, y, and z, whatever is there, is represented with a position vector r, this, and with its tail at the point. So remember in 2-space, a position vector meant it started at 0, 0. Now, in 3-space, it really doesn't make sense for vector fields for all points to start at 0, 0, 0, and instead this says that whatever function you decided to plug in and find the force of, the vector that you find starts at that point, which means the tail of the vector is at x, y, z, whatever point you plugged in to this equation. So one of the first things you have to find when the question asks you to describe is whether or not it points inwards and outwards. And if you see here, since all of the variables, which means the components I, j, k, are positive, because if x, y, z is positive, then the vector will be pointing in the positive direction. If x, y, z is negative, then the vector will be pointing in the negative direction, which means that 1, the vector field must point outwards. Okay, so that's the first pattern, and the second one will deal with magnitude and how that changes as the points change. So as you see, this vector directly corresponds to what the coordinates are. So if x grows bigger, y grows bigger, and z grows bigger, the components of the vector will grow bigger, and therefore the magnitudes will grow bigger, which means that the magnitude increases as x, y, z coordinates increase. So as I said before, we're not going to graph it, and instead we're going to look at patterns based on just the equation and the coordinates. But you'll notice that if you envision this vector field, it's actually kind of the opposite of a gravitational force field. As you recall from earlier in the video, I talked about how all the forces point inwards and the forces grow bigger as the x, y, and z coordinates grow smaller. But this time, actually, it's the opposite. The vectors point outwards and the magnitude increases as you go out, which means the x, y, z coordinates increase. And so the last thing we'll observe is about the overall pattern, and as I said before, if x, y, z coordinates are positive, then the vectors will be pointing in the positive direction, and if x, y, z coordinates are negative, then it'll be pointing towards the negative direction. To clarify what I was saying, pointing upwards and downwards is in terms of the z direction. So a better way of phrasing it is that the vectors point downwards if it's below the xy plane, and the vectors point upwards if they're above the xy plane. If you want to check that, it's very easy to just plug in the points 1, 1, 1, and then the points -1, -1, -1. And that's it for this example. Now let's move on to our last example, and this example is asking you to find the formula for the vector field shown below. And this is shown in 2-space actually, so it's going to be a lot easier than finding the pattern in 3-space, which is really hard to write a formula for if it's not like the formula seen in example 2, which is just x, I, y, j plus zk. So since the vector field is in the xy plane only, you know it's only a function of two variables, which is x and y, so you don't have to look for z. And to find a formula for it, you need to find the pattern in the different vectors at different points. So there's two steps towards doing this. The first step is to look in this direction, which is in the y direction. And as you can see, just follow one line of coordinates. Let's follow this. It's actually kind of hard to see, but you can see that the magnitude of the vector increases as y increases. So that's one part to it. And the second part is if you look in this direction, so basically follow x. And let's follow this line. And again, you see that the magnitude of the vectors increase as x increases. And typically to represent a formula, you use this notation for the function. And as we talked about previously, the vector's magnitude increases as y increases and also increases as x increases, which gives rise to this vector field formula, which is xi plus yj. So as you see from what I did, it's not always about plugging a number in and finding the specific vector. Sometimes it's just about pattern. Actually, you see pattern in all three examples, and that's the key part about understanding vector fields, is just understanding the pattern in which the vectors exist at different coordinates. And that's it. Thank you.